Chapter 14, Section 7, Oxidation of Sulfur Compounds. When it comes down to it, okay, we got to keep in mind, carbon's not the only thing out there. Many organisms are going to be utilizing sulfur or sulfur-containing inorganic compounds. These guys are going to be chemolithotrophs. Take up chemicals, but they're going to synthesize, using alternate mechanisms than what we've covered before. Hydrogen, or is it hydrogen sulfate, thiosulfate, sulfite. The changes from one form to the next the oxidation is going to go, and you're going to see different levels of energy from the reduction of, the oxidation of, from one to the next, to the next, to the next, to the next. So as you go through this, different excited electrons can be pulled off to reduce NAD to NADH, and then, others, excited electrons could be pulled out to be transferred over to an electron transport chain so that you can set up a proton motive force, and so you can synthesize ATP. All of those that can then go to the litho portion right here. What's interesting is when you go and you look at the sulfur, when you get just to plain old sulfur, hydrogen sulfide broken down to sulfur. Sulfur has to be stored. It's insoluble. So it's going to be stored in the cell. Why store it? Well, because you can take the sulfur and you can turn it into thiosulfate, thiosulfate to sulfite, sulfite to sulfates. And as I said, as you're going through these different series of sulfide to sulfate, or sulfite, SO32, to SO42, thiosulfate, S2O3, to sulfate. How many electrons can be pulled out of that reaction, that series of reactions, which can then be utilized in carbon fixation? And look how much energy, how exergonic this reaction or this series of reactions is. So there's a lot of energy here in the sulfur-containing compounds. And you look here, what you're seeing here are either sulfur granules or sulfur crystals that are attached to the cell. Either it's internal structures or external structures. The sulfur, after the hydrogen sulfide has been broken down, still has a lot of energy or a lot of reduction power, oxidation power there. To do any of this, though, you're going to have a series of genes in the gene products, the proteins known as SOX, SOX, sulfur oxidation systems. Okay. SOX XA, SOX YZ, SOX B, SOX CD, X and A, Y and Z, CD form complexes. Individual protein products have to come together to get sulfur dehydrogenase, or a carrier protein. These will go through and will oxidize, remove the electrons, which will then be funneled to a form of electron transport chain. Not exactly the same electron transport chain you've seen in previous, but it's a similar theme, a similar production. And no, I'm not going to go through all of this. What I want you to focus on is the reductase, sulfur HS, SO3, and you go through SO4, SO4, and in the process, 2 electrons here, 6 electrons there, 2 hydrogens get pumped, 2 hydrogens get pumped, 2 pumped, 2 pumped, 3 to 4 flow back through, ADP to ATP. And you just keep going and going. Up here, getting sulfur into the system, into the cytoplasm from outside. Here's the periplasm. Here's the cytoplasm. So to get it in the periplasmic space between the 2 membranes, and there where it's going to be altered, here's where the SOX proteins come into play, specifically SOX Y and Z. Now, am I going to go through all this? No. Am I going to expect you to be able to sit there and tell me all of this? No. Am I going to expect you to sit there and be able to tell me overall what is occurring here, how sulfur compounds, H2S, is then going to be, turned into sulfite, ultimately sulfate, and in the process, boom, boom, boom? Sure. So as I said, you will find that many of these prokaryotes will store sulfur. Okay, they can't get rid of it, or they can only take its oxidation reduction to a certain point, and then it stalls. Well, sulfur oxidizing microbes that store sulfur granules. Okay, they're storing sulfur instead of taking it all the way to sulfate and then getting rid of it, which means they are missing the dehydrogenase, the SOX CD. So they got some of the SOX gene, some of the SOX operon, but not all of it. Transport from into the cytoplasm, DSRAB. So you can end up with sulfite, or sulfate, sorry. So certain proteins, certain genes beyond just the SOX genes, SOX proteins, are utilized in the movement of the sulfur-containing compounds from the environment to the periplasm, modifications of the periplasm, transport into the cytoplasm. The reverse electron transport, what we've talked about before, where it's not taking it from a high down to a low, and then as it's being passed, pump, pump, pump. Now here it's going to be a bit different. It's the flow of the hydrogen or the electrons or whatever across the membrane are pushing or exciting an electron itself, and then you're going to get NADH is reduced, or NAD is reduced to NADH.